So we have started the recording, and I will also start the backup recording. Okay, so we are set now. I'll go to the writing app. Okay, so on Monday we were discussing how to find out the distribution of the shear stresses for a beam with a rectangular cross section. So this kind of cross section. And I'd mentioned that if we have to use this particular formula, this tau xy is equal to tau yx is equal to minus vq by it, the real brain work involved here is just involving how to find out this q. That is the first moment of area for the part of the cross-sectional area under consideration. Under consideration means if we wish to find out the tau yx here or the tau yx here and the tau xy here, then this is the relevant, this hatched part is the relevant cross-sectional area. So going forward, let me just quickly write down the expression that we are going to obtain after we simplify this and sorry. So this is the expression that we are going to get, half b h squared by 4 minus y squared. Simple algebraic simplification. This is the expression, and if we substitute that in the expression for tau xy, we obtain minus vq by it is equal to, the v remains as it is because that is something which will be either given or obtainable from the free body diagram and everything. You know how to obtain the v at any particular cross section. Q we directly substitute from here. The I, yes.
Sir, I have a doubt. So like, so shouldn't it be like h by 2 minus y into h by 4 minus y, h by 4 plus y?
Say that again.
So like, shouldn't it be like a b into h by 2 minus y into h by 4 plus y? Like, how do we get this a square minus b square kind of expression?
No. So we get this expression. I did it myself. Let me just check one second. Yeah, we get this expression. You please check yourself.
So like, I am able to understand. So like, we have h by 4 plus like 1 y by 2 in the. Sorry, I got it. So it's okay.
Okay, so all right. I is 1 by 12 b h cube t, and then for the q I have half b h square by 4 minus y square. So effectively what this will give us is, oh, I forgot the minus. So I have minus, so this 12 into this gives me 6 v, this b and this b will cancel, and I will end up with actually this t happens to be equal to b. So I'll be left with another b here. So effectively I'm getting this as bh cube in the denominator, and then in the numerator I will have h squared by 4 minus y squared. This is the expression for the tau xy as it varies along y. Now this is an important expression, but we are going to look into it a little bit more closely in the sense that we first want to see what is the maximum possible magnitude of this tau xy, or the maximum possible value. The tau xy, if you do a little bit of analysis here, or if you're good enough with calculus, you can probably do this in your head. You're going to obtain the highest value of tau xy at y equal to 0. So the max magnitude is here. This is minus 6v by bh cube, h square by 4, which is basically minus 6v So the way that I want to write this is wait. This is BH. This is 2. I want to make that a 3. So it's something like this. That is minus 3 by 2 times V by BH. Now, if you look closely at this expression, this V divided by B by H, that is the tau average. Okay, that is the average value of the shear stress over the entire cross section. It is something like this, that the V is applicable over the entire rectangular cross section. The area of the rectangular cross section is BH. So force divided by area, that gives us an average estimate of the shear stress, that is the tau average. So what it is telling us is that the tau max magnitude, that is equal to 3 by 2 times the tau average value. Okay, this is important to understand, because if we were to grossly approximate our tau average by this, then the maximum value of this thing would be 150% of that value. Okay, so there is a significant amount of difference between the maximum value of the shear stress over a cross section and the value that you would otherwise obtain from a simple averaging. Furthermore, the minimum value of the tau xy, that will be occurring at the top and the bottom cross sections, or the top and the bottom edges, that is going to be equal to 0. And it makes sense because at the top edge, if we say that the tau xy value is equal to 0, it means that, so look at it this way, that at the top edge, if we say that the tau xy value is equal to 0, so this value is equal to 0, it also means that this value, the tau yx value on the top surface, that is equal to 0, because these are two complementary values. They have to be equal to 0. So when we use the word complementary in the context of shear stresses, there is nothing. This complementary thing. It has nothing to do with pi by 2 minus something like we used to do in our school level geometry. Please note that. Okay, this is just a terminology that is used by people interested in solid mechanics. They just say that the shear stresses on two perpendicular faces, they are complementary to each other, meaning just that they have different directions, but their magnitudes are the same. Okay, so on the top surface, this shear stress value, the tau yx, that is also going to be equal to 0, and that makes physical sense because on the top edge of this beam, there are no shearing forces acting. Okay, for the problem under consideration, there are no shearing forces acting, so it makes sense to obtain this value. It is perfectly all right. But there is another thing to note here. Just like we have found out that there is a certain distribution of the tau xy as we move along y, and that is a quadratic dependence, and we can actually plot this out. We can plot this out in this way, that suppose we say that this is our y, this is the 0 value, and this axis, it represents the tau xy. So if we plot out this thing, if we plot out tau xy is equal to minus 3 by 2, well, I want to plot out the magnitude, okay? So we don't have to go to the negative axis. So this is going to be 3 by 2. So if you just look at this expression, it is not 3 by 2, it's 6v by bh cube. Let me just write that. 6 mod of V by BH cube, and then I have this h square by 4 minus y square. H square by 4 minus y square. So when we plot this thing out here, we are going to obtain a parabolic distribution. This here, this value, that is this value. So this is 3 by 2 absolute value of V by BH. This is 0 and this is 0. So this is minus h by 2 and this is of course h by 2. So just like we have this kind of a parabolic distribution along the y direction, you should try to appreciate that along the z direction also. What I mean by z is that it is this direction. Okay, so remember that this is x, this is y, and along the neutral axis you will have the z. So along the z direction also there is going to be a distribution. Okay, it is not going to be a uniform value. So this distribution is along the y direction. What I'm going to talk about now is the distribution along the z direction. And that distribution, it will look something like this. At any particular level, that distribution is going to look something like this. Okay, so these are the values of the So I lost the connection there for a second. I hope all of you can hear me still.
Yes, sir. Like for some seconds, the audio was not there.
Yeah, for a few seconds it got lost. So as I was saying, this shear stress distribution along the z direction, it looks like this. And you may be a little bit surprised to know that the maximum value of the shear stress along the z direction, it occurs on these vertical edges. Okay, the absolute edges. The minimum value is actually at this thing. We can try to go about finding this thing, but the current level of modeling that we have done, that will not enable us to obtain this value, this distribution. So we will have to appeal to theories of elasticity, which you will study later on, probably in your 4th year, which will enable you to obtain this distribution. So right now we'll just be satisfied with knowing, just like general knowledge, that this kind of a distribution will appear. At the same time, it is important to appreciate for what kind of beams this, despite the fact that this is the real distribution, it is quite all right to talk about the shear stress in this particular form. So for what kind of geometry? So when you have B by H less than 1 by 4, so when the width of the beam or the breadth of the beam is not too much compared to its height, then even though the actual distribution theoretically may be looking like this, it is all right if we say that the average value of the shear stress along the z direction is captured by this. Okay, so at any particular value of y, the average value of the shear stress along the z direction will be given by this formula. Okay, this is an approximation, but it holds true as long as, sorry, this should be B by H, okay, not B by 4. As long as B by H is less than 1 by 4. Okay, so valid along Z direction. If we have this, this relation. So that is why you must understand that any particular y level along the z direction, this tau xy is actually giving us an average value. Okay, so it is like tau xy average along the z direction. Very, very important to appreciate this. Next, what we are going to talk about a little bit is a different kind of cross section. Because just like we had a couple of important things to say associated even with the simplest of the geometry of the beam cross section, that is a rectangular geometry. So also for the next kind of geometry, which is a very common kind of geometry, we'll have some special things to say, and that is the I-beam. So this time I'm going to just draw the cross section. This is a widely used in practice type of cross section. It looks like the English letter, capital letter I, but it also has some other names. It is sometimes referred to as the American Standard Beam, or sometimes it is also referred to as the wide flange beam. There are certain subtle differences between the American Standard Beam and the wide flange beam in terms of its dimensions, but at this point, let us not digress from what I want to discuss in terms of the shear stresses. So just like in the case of the rectangular cross section, we considered different levels of y at which we found out tau xy. So also it is very much possible to determine the shear stresses at different levels of y from the neutral axis. So understand that the neutral axis, because this is a doubly symmetric cross section, it will be passing exactly through the centroid of this thing. And we are going to calculate, or we are going to consider this particular distance, the upward direction, as y, as we have been dealing with earlier. Now, unlike the rectangular cross section, there is a variation in the geometry along the y direction. In the rectangular cross section along the y direction, there was no variation in the geometry, but here we do have a variation in the geometry, which means that the expression of the tau xy, it is going to be slightly different in different sections. Of course, it was different in the at different levels of y, even for the rectangular section, but you were able to obtain just one expression. That's what I meant, that you are going to obtain different expressions in these different zones. But the good news is that because this cross section is doubly symmetric, that is, it has both left-right symmetry as well as top-down symmetry, it will be enough for us to obtain the expressions just in this zone, in the top zone, and in this thin middle zone. Now, just for the sake of terminology and some general knowledge, please note that for an I-beam like this horizontal portion at the top, these two things, they are referred to as the flanges. Okay, so they are these are the flanges. These are the flanges. Let me just write them down. So these are the flanges, and this vertical section in the middle, that is referred to as the web. Now, I don't know the history behind why these things are called like this, because calling this vertical part as a web, I don't know the reasoning behind it. Okay, but it is what it is. So this vertical part is the web, this horizontal part is the flange. Now, in the flange, you are going to have one expression for the tau xy, and in the web you are going to have another expression for the tau xy, and there is going to be some jump in the distribution of the tau xy also, and we're going to look at it. So first of all, even if we don't write down the actual expressions, please try to understand the procedure is exactly the same as before. So we start from the top, and then we take a cut at a certain portion. We take a cut at a certain portion, at a certain level of y. We considered this particular section. Again, you understand that this dimension is b, and perhaps you can say that this height is h, or maybe the entire height is h. It doesn't matter. So these dimensions will be given to us. This is t, let's say. It could be T1 and T2 here, but for the sake of simplicity, we can say that this is T as well as this thickness is also T. Now, more generally, these two thicknesses will be different. So when we calculate our y like this, we are going to get one expression, and alternatively, when we take perhaps let's say a section here, we are going to obtain a completely different kind of thing, completely different kind of expression. So what is actually found out is that if we again draw our y-axis like this and our tau xy axis like this, then let's say this is our height h by 2 and this is minus h by 2 and this is t. So let me just clear up that drawing a little bit. So that is h by 2 plus t over there. So on that, the distribution will be something like this. It's going to be a parabolic distribution, but with a very low value. And then when this web portion starts, when you're moving down and this web portion starts, the tau xy value is suddenly going to jump up. And then it is going to be another parabolic distribution, but almost a constant value. So the curvature here is very, very small, or the radius of curvature of this curve is very, very large. And then it is going to be symmetric, something like that. And then it's going to again fall down. And then it is going to be like that. So this is minus h by 2 minus t. So this portion. If you wish, you can go about finding the expressions here. I will not do that. I'll leave that as an exercise for you. If you have any problems, you can ask me. There will be problems involving this thing, but there are certain things which you probably will not be able to realize yourself, even if you manage to find out the expressions. And it is those things which I want to emphasize as part of this class. The first thing is that when we are drawing this kind of a profile for the tau xy along the y direction, again you must understand that we are obtaining these plots or the corresponding expressions by considering this mid zone. Okay, we are obtaining these expressions by considering this mid zone. So what I actually mean to say is that this neutral axis is directed along the z-axis. Okay, the z-axis is like this. So along the z-axis, there is going to be a certain variation in the tau xy, just like there was variation in the tau xy along the z direction for the rectangular beam also. So this is some kind of an average value. Furthermore, you note that if you focus your attention on this level, okay, on this bottom part of the flange. Now on the bottom part of the flange, the tau yx value is going to be 0 because there are no shears, there are no shearing forces acting on this part or on this part, which means that the tau yx value there is 0. Just like we had said for the rectangular cross section, that at the top surface the tau yx value is 0. So also it is 0 here. But you are saying that tau xy is having a non-zero value at this y is equal to h by 2. So that is happening because if you are focusing your attention somewhere in this part near the middle of the I-beam, then you are going to have a non-zero value. But if you move here at the remaining at the same y level, if you move here, then because tau yx is equal to 0, tau xy is also going to be equal to 0. Okay, so it is something like this, that you have the I-beam like this. Because on that bottom surface, the tau yx is equal to 0, so also the tau xy is going to be equal to 0 here. That is what I'm saying at this part. But at this part, the tau xy is not equal to 0. So this is 0, but this is not equal to 0. Furthermore, there is a significant jump when you are just above this level of h by 2. So consider y is equal to h by 2 plus here, and y is equal to h by 2 minus. Just when you are moving into the web, there is a significant jump between these values. There's a discontinuity here. Okay, that is happening because of the thin or the thinness of this web geometry. Okay. Another thing is that, as I've already mentioned, the tau xy value over the length of the web or over the height of this web, it is of course having a y dependence, but it is not too much. So for all practical purposes, even if you consider, if you approximate this to be fairly constant, is not a big mistake. Another very important thing to note here is that there is a very sharp corner present here. There is a very sharp corner present here. So if you actually solve for this using the theory of elasticity or other sophisticated methods, you will find that at this corner and at this corner, there is a significantly high value of the tau xy, which is not captured by this particular theory that we have developed here. Okay, so these types of sharp corners, they are referred to as the zones where you have something called stress concentration. Okay, so this will be the zone where you have something called stress concentration. They can give rise to very high values of the stresses, these kinds of corners, which is why in real practice, when these beams are actually fabricated for practical use, they try to make these things to be slightly smooth. Okay, they artificially make these things to be slightly smooth, like this. Furthermore, you have sharp corners here, so they try to smoothen this thing out also. They try to smoothen this thing out also. Here also they try to smooth it out. Here also they try to smooth it out. So that as few places as possible, they try to have smooth these sharp corners. Because of the necessity of the flatness of certain structures, it may be required to have this kind of a sharp corner that may not be done away with. So what you need to have, you have to have, you can't get away from it, but wherever you can avoid, you try to make it smooth. So in those regions, your current theory that we have presented here, that we've discussed here, that is not going to hold. Okay, but as long as you stick to the middle of the geometry, the tau xy expressions, the formula that we have, or the procedure that we have, that will be fine. Okay, this is about the American standard beam or the wide flange beam, more generally the I-beam. We can of course have other kinds of geometry also, the T-beam. We can also have beams whose sides are not straight. Now, right now, I don't want to go into a discussion about that. Maybe as part of our problem solving exercises, I will discuss as an illustrative example is circular geometry. But right now, what I want to go into is something related to this shear stress formula, very closely related to the shear stress formula. But through that topic, I will be able to discuss something which may enable you to get a different viewpoint of the importance of shear stresses. Okay, in the actual design of beams. So that topic is referred to as shear flow. Now, when we first study about shear flow and we look at the textbooks, it can become a little bit of a confusing thing, because shear flow, depending on the context, can mean different sorts of things. And we will see the two different aspects of the shear flow. So one of these things, the shear flow, has to do with a direction which is parallel to the longitudinal axis of the beam, and the other shear flow that we'll be talking about will be within a cross section. So first of all, we are going to talk about the shear flow, which is along the length of the beam, parallel to the longitudinal axis of the beam. So what is this shear flow, and how does it come into being, and why does it have such a close connection with the shear stress, and why even do we talk about things like flow? Okay, so through this subsequent discussion, let me see if I can try to clarify it. So for this, again, take your mind away from all these equations and everything, all this theoretical business, and try to think of it, try to think of the beams as they are fabricated in a practical scenario. You see, no matter if we have different kinds of standard cross sections, depending on the actual necessity of an engineering situation, it may be required to build certain special kinds of beams or build up certain cross sections of beams made up of this unit building blocks. What I mean to say is that, for instance, we have talked about this kind of a T cross section. We have come across this in our previous chapters. Now, even this T cross section, you can think of it to be built up from two rectangular cross sections. This is one rectangular cross section, and this is another rectangular cross section. They may themselves be used to make up beams, but no, what we are doing is we are joining them together in such a fashion that we are obtaining this T cross section, this T-shaped cross section, and this T-shaped cross section, we are using it in the form of a beam. So what is happening here is that we are using it in this particular form. Something like that. It is very much possible to extend this idea further along and to build up more complex shapes by further adding on to this type of a cross section more bits and parts. For instance, you may think of a cross section which is further augmented by two bits like this. Correspondingly, you will have the addition here like this. Again, you understand that this is just a rectangular block that we have attached here. So this way of building up more complex shapes as per the requirements of a particular engineering situation, this is literally referred to as built-up beams or built-up cross sections. Okay, this is the key word here, built up. So what is the importance of shear stresses and shear flows here, or shear stresses? You see, it is just one thing to draw these things like a children's diagram, but when you have to actually fabricate this, you have to understand that you have to really have some means of attaching this rectangular block to this rectangular block, and of attaching these rectangular blocks to these things. So how do you attach them? Well, you can put in some bolts, you can put in some nails, you can use even some kind of an adhesive or a glue to attach them. Okay, actually for wooden blocks, Fevicol is a good adhesive. Okay, it is actually used to join together two blocks of wood. Or they may be even welded together. So various means are there of making up or fabricating this built-up beams. And this is where in these zones where the attachment is taking place, that is where the importance of shear stresses becomes immensely significant. You see, earlier we had as part of our derivations, we had seen that we wanted to find out the tau xy. The tau xy would be able, so we wanted to find out the shear stress distribution in the vertical direction within a particular cross section. So we wanted to find out these things. We wanted to find out this tau xy. This was our tau xy. Okay, or perhaps in the reverse direction. I should be faithful to the positivity convention that we have been using all along. So this was our tau xy distribution that we were interested in. But when we found out this tau xy, we took up an indirect route of arriving at this expression of tau xy by first obtaining an expression not of the tau xy directly, but of finding out the tau yx. And that tau yx, it appeared on a horizontal level. What I mean to say is that you can perhaps think of this particular geometry only and separate out this part. If you separate out that part, just imagine that it is detached from that cross section. Just think of it like this. So as if it has been non-glued or unbolted, and you are considering this separately. So here you will have the presence of the tau yx. So it will be something like this. You can have a tau yx like this. Okay, that's better. So tau xy like this. On this particular horizontal level also, if you detach or detach this, you will be obtaining some kind of a tau xy there. So from the point of view of the strength of the attachments that are required or the spacing of the bolts that may be required, this kind of information is of immense importance. Okay, so when this kind of beam is under bending, there will be a significant amount of tau xy. This is tau yx. The tau yx here, the tau yx here, the tau yx here, which will be responsible for failures, for potential failures along these joints. I repeat, whenever this entire beam is under bending, then this kind of a tau yx will be responsible for a potential failure along these attachment points. What I mean by potential failure in the very simplest of terms is that if the tau yx value, it increases too much, then it can so happen that the adhesive that is present there, it comes completely detached. So this part of the beam can come out completely detached. This part of the beam can come out completely detached. This part of the beam can come out completely detached if the tau yx value increases beyond a certain threshold value. So it is extremely important for the structural integrity of the beam, for the structural safety of the beam, that this tau yx values do not get too much high. That is why we need to understand what these tau x values are. And we have already found out a way of finding out this tau yx values. So whatever expression we have found out till now, that is for tau xy, that is also for the tau yx. But when we are taking a look at the structural safety of the beams from this particular perspective, not from the perspective of the tau yx in this vertical face of the cross section, rather in a direction which is along the longitudinal axis of the beam. So you understand that the longitudinal axis of the beam is this x. So these shear stresses tau yx, they are along this x direction. So these kinds of shear stresses are parallel to the longitudinal axis. They are very important. Okay, so what we require for the purpose of design calculations is not actually the value of the shear stress themselves. Rather, what we require is the force per unit length associated with this shear stresses. I repeat myself. What we actually require for the purpose of designing these beams in such a way that their structural safety is maintained in the sense that these shear stresses do not exceed too much in value, the information that we really require is not the actual value of this shear stress. Rather, what we require is the force per unit length which is associated with this shear stress. So what we'll do is we will just write down the general expression of the tau yx. This is our tau yx. This is our general expression. Now, this is the shear stress. Suppose I take this T back here. This is going to look like minus VQ by I. Now, this thing, you understand, has the dimension of force per length. So it is something like this, that you have the tau yx here and you are multiplying it by the thickness here. So what you are obtaining really is the force per unit length which is parallel to this x direction. So the per unit length, that length is along this x direction. So this force, this is the force per unit length. Sorry about that. My writing app again misbehaved. So I'll just start it again. And I hope everything is fine. Yeah. So I'll just save this again. Okay, so as I was saying, this is force per unit length, and you can actually check by writing out the dimensions on the right hand side that this is so. Now, as far as the theory is concerned, all that you have to recognize is that this force per unit length, that is what is referred to as the shear flow. Okay, so the shear flow is actually just another term for this force per unit length. So this thing is just referred to as the shear flow. It is called the shear flow only in the context of these kinds of beams that we are talking about, and only when we are talking about the force per unit length, where the length happens to be along this kind of a direction. Okay, but there is another aspect to this shear flow which we will discuss. Before going to that, I just want to highlight that this force per unit length calculation, or the shear flow calculation using this minus VQ by I, as far as the actual procedure is concerned, you don't have to do anything separately compared to the previous procedure. Okay, the same kind of idea will be used to actually calculate this value. So in terms of procedure is nothing new, but in terms of the perspective of understanding the things, it is something different. At the same time, you must also appreciate that I have talked about attachments which are along horizontal planes, but it is very much possible that we may have a different kind of attachment. For instance, we can have a structure which is something like this. So this is just a rectangular block. Now on this block, what you do is you attach a vertical block like this, another vertical rectangular block like this. Okay, so you see here the point of attachments of the different rectangular blocks was along horizontal planes, but here the point of attachment or the zones of attachment, they are over this vertical planes. Okay, this is the vertical plane over which the attachment is there. So okay, so perhaps you have nailed these two things together, you have nailed these two things together, or you have attached some favicol along this, you have attached some favicol along this, and you have joined this thing to make it look like a table. Okay, so this rectangular thing is the table top, and these are like the walls of the like the table. Okay, some kind of a maybe a dining, not a dining table, maybe a like a drawing room table or something. Now, this may also be subjected to some kind of bending moment, and when that happens, there will be some kind of shear stresses developed on these vertical zones also. Now, please note that on those vertical zones or those vertical planes, the shear stress that is developed, if you consider your y-axis to be like this, and your z-axis to be like this, and your x-axis to be like this, then those vertical planes, they are parallel to the xy plane, and the unit outward normal to that is along the z-axis. So the shear stresses that we will be actually be concerned with is not the tau yx, rather it will be the tau zx. Okay, so suppose you are considering this zone, so the shear stresses that you would be concerned with will be the tau zx. Now, please note that we have obtained this formula by considering the tau yx, but if you try to find out an expression for the tau zx by again doing a difference between the sigma xx plus delta sigma xx minus sigma xx like we had done earlier, you will again end up with this kind of an, okay, this vq by I. You may or may not end up with the minus sign depending on the way that you have set up your coordinate axis and which plane you are considering, but the magnitude of this tau zx, that will be this absolute value of v times the q divided by I. Of course, tau zx times the thickness, that you have to remember. So the shear flow that will be associated on these vertical planes, that will again be equal to vq by I. Okay, you may or may not end up with a plus or minus, but that plus or minus sign is only being consistent with the choice of your coordinate of your coordinate axis setup. In terms of the actual shear forces, the plus or the minus sign, it really doesn't matter. As long as you recognize the direction of the shear flow correctly, that plus or minus sign actually doesn't matter. In fact, professional engineers, when they write down shear stress values, they never use the negative sign. They have to be very specific about the direction of the shear stresses, but they never write the minus sign. Okay, because the minus sign, without actually referring to any particular coordinate axis, it doesn't make any sense for the shear flow, or for the shear stresses. Okay, we'll talk about the significance of those plus and minus signs in the next chapter when we talk in detail about transformation of stresses. But for now, this much is sufficient. Now, very closely connected to this shear flow concept associated with this tau zx is the next thing that I'm going to discuss with shear flow. So please note, I want to highlight again, here we are talking about the horizontal planes, here we are talking about this vertical planes, and we are talking about the force per unit length. But the next shear flow thing that we are going to talk about, that will be again coming back to a particular cross section. I'm running short of time here, but I'll try to finish this thing up. So people who have a next class after this or wish to join may do so. If you students are present here, I won't mind if you just leave, okay? But given that we have already lost 2 hours, well, not lost, but we have utilized those 2 hours on Wednesday for test purpose, I would like to finish this next topic up also. It's not a long topic, but I'll try to finish it up so that further along, we can go on to problem solving.
Hello, sir.
Yes.
So here for the shear flow in the vertical one, the I will be what?
I will be for the entire cross section.
Okay, sir.
Okay, so we are considering this entire table thing as a beam. All right. Okay, so moving on. Just to distinguish between the previous topic and this one, I will call this as shear flow distribution. But it will be more useful if I just write this as along the length and this thing as within a particular cross section. Okay, so now I will again draw the I-beam. I will draw the I-beam, but in a three-dimensional configuration. So something like that. Now, let me also set up my coordinate axis. This is not good. Okay, that's better. This is X, this is Y, and this here is our Z. All right. Now, what I want to do is I want to take a vertical cross section, not a vertical cross section, rather a vertical cut at some distance away from this vertical edge of the flange. So I will take a cut here and I will separate out a little chunk from this corner. I will do that by again considering a cut like this here, so that overall I end up with a little thickness which is like this. So I take a cut along the X direction and I take another cut along the Z direction, so that overall I end up with this little block here. So I'll separate that out. Now, we have to understand that on this face, just like before, we are going to have a sigma xx plus delta sigma xx. Please note that whatever I am going to do here, it will be exactly the kind of thing which we would have to do here. The only difference is that here we were interested only along the length, but here we'll be talking about things within this cross section. Okay, so just wait until you see what I'm going to obtain at the end. So on the back face, on this back face, I'm going to have this sigma xx. Now, because there is a discrepancy in the value of this sigma xx, and the sigma xx plus delta sigma xx, that discrepancy is going to be adjusted by another horizontal force which is associated with this shear stress. So that shear stress is what? That is the tau zx. Okay, the unit outward normal to this face is along the positive z, so the shear stress direction must be along the positive x. If we write the force balance associated with these stresses, these normal stresses and this shear stress, then what are we going to obtain? Please also note that since we are considering this entire chunk, there is no contribution that will be given by the tau yx. The tau yx would have been present here on this top face and on this bottom face, but please note that those are actually free faces. Free faces means on that face there is no shearing force. On the bottom face also there is no shearing force. Those are completely free of shear, so there are no shear stress contributions from the top face and the bottom face. That is why we are not depicting those. Okay, so the force balance associated with these different stress components will be like this, and this will be familiar to you from what we have been doing earlier. This A dash area is this area, okay? This area. So the direction of this sigma xx plus delta sigma xx, that is the same direction as this tau zx. So we write the contribution to the force along the horizontal direction or along the x direction from this tau zx by noting that this distance here, that is delta x. Okay, so if the thickness here, okay, so if this thickness here, this is T, then we are talking about T into delta x. The direction of this sigma xx is along the negative x direction, so it will be on the other side. So this is going to be equal to integration sigma xx dA dash over the same kind of area. So we are talking about that area. Okay. So this is the force balance, which means that our tau zx T delta x is going to be equal to this sigma xx and this sigma xx cancels. We are going to be left with minus delta sigma xx dA dash, like that. And just as before, we take this delta x down there. So this is tau zx T is equal to minus delta sigma xx divided by delta x dA dash. And this thing in the limit that delta x tends to 0 is going to give us minus of d sigma xx dx dA dash. We move on to the next page. Tau zx t is equal to, so from here we are going to obtain d dx. So sigma xx is equal to minus my by I. This is from our earlier chapters. So this is exactly following the kind of derivation that we had done earlier for the tau yx. And you see this minus and minus cancel. And I will quickly write down this thing as dm dx y by I over this cross-sectional area A dash, this I does not vary. This dm dx is equal to V, and that V is also a constant over the cross-sectional area. So what I obtain here is this Vi integration y dA dash, and y dA dash over the area A dash, that is nothing but the first moment of area, the familiar thing which we have been discussing till now, that is the Q. So this is again coming out to be VQ by I. So you see this tau Zx by T, we are obtaining that as the shear flow. This is exactly the same thing that you would have to do, like literally exactly the same thing which you have to do for this. You see what I have obtained here, it is exactly that what I have obtained. But right now, I am not going to be satisfied with this shear flow thing in the lengthwise direction. Rather, what I'm going to say is that this shear flow, okay, so suppose I call this tau Zx times T to be a shear flow, and I depict it by the small letter q. This q is acting along the x direction on this face, but that means that there will be a corresponding tau xz on this face also. Okay, there's going to be a corresponding tau xz on this face also. Please note that on the top face there is no shear, on the bottom face there is no shear. But when we are talking about this face, it does not mean that there is no shear. I have taken a cut section at some point in the middle of the beam and exposed this face, but it does not mean that I mean there is very much a V, a shear force present all over this cross section. So the tau xz that I will be drawing here, okay, the tau xz that will be present here. So this is our tau xz. That tau xz value will be exactly equal to this tau zx value, and the shear flow associated with the so this is what I want to write. This is the shear flow Q associated with the tau Zx value. Similarly, the shear flow associated with tau Xz is going to be equal to that associated with tau Zx, that is VQ by I. This VQ by I that we have just obtained associated with the tau Zx. So think of it like this. We have our I section, our I cross section like this. Now I am drawing a front view of it. We are obtaining a shear stress distribution like this. This is our tau xz, or the Q associated with the tau xz. We are obtaining this because we took a cut section in this fashion. Had we taken a cut section somewhere to the left, we would have obtained another value of the shear flow. Now, if you had started from this left hand side, you would have similarly obtained a shear flow like this. And if you had kept on taking different kinds of cut sections like that and like that, you would have kept on obtaining different values of the shear flow like this. You can keep on doing that until you reach this middle point. After you reach this middle point, you go down. When you go down, you will take a cut section which is like this, which is along a horizontal plane. When you do that, you are going to obtain a shear flow which is associated not with tau zx or xz or any of those things. Rather, you are going to obtain a shear flow which is associated with tau xy. You are going to obtain a shear flow like this. Again, if you keep on taking different cut sections along this horizontal planes, you are going to keep on obtaining the shear flow associated with the tau xy. But when you move down, you are going to obtain shear flow again within this flange zones. You can obtain these things like this. Okay, I drew it in this fashion, going from the top down and bottom down like this, because I wanted to emphasize to you the significance of the word flow. You see, it is as if you have let water run from these two directions. They are joining up, meeting like a joint stream, and then it is running down, and then it is subdividing like this. Okay, it's almost like the flow of water from here to here. There is no flow of water in reality, but you can imagine that the distribution of this Q is in such a fashion that it almost gives the feeling that water is flowing and joining together and then subdividing. Okay, it gives us a very intuitive way of looking at the shear stress distributions, or more commonly as it is known, the shear flow over a particular cross section. Why is this important? Is it just a fun exercise? It is a fun exercise to think about it like this, but there is also a certain usefulness as far as actual engineering practice is concerned. That is because this is just one type of cross section. You can have another type of cross section, and there also this kind of an intuitive understanding regarding the shear flow can give us a very good idea about the distribution, about the qualitative nature of the distribution, in various kinds of cross sections. So had this been an actual live class, I would have been able to ask you certain questions. Let me see if anyone is here. We have a few people, but I don't know if they're actually present. So it's something like this, that if you again appeal to that idea of water flowing, you will understand the shear flow will look like this. It starts from the two ends of the flange, it joins up together, and it gives us this value. Now, it will be very important for you to understand that ultimately this shear flow should shape up in such a fashion that the net contribution from this is going to be equal to V. It cannot be that the shear flow shapes up in such a fashion that the shear stress distributions, they exceed or they are below the value of V, because these shear stresses, they correspond to the actual V, the shear force which is acting on this cross section. Now, because these are horizontal contributions, they cancel each other out in effect. Okay, the net effect of these two is to just cancel out each other. So it is this vertical contribution which is going to be equal to the net vertical contribution due to this entire shear flow distribution, that is going to be equal to V. Similarly here, this distribution and this distribution, they are going to cancel each other out. This distribution here and this distribution here, they are going to cancel each other out. Ultimately, it is the contribution from this web portion which is going to be equal to the V. You can have more interesting cross sections like this. Suppose a triangular cross section. Here, you are going to have a distribution of the shear stresses which are parallel to the directions or parallel to the sides or the edges of this cross section, and here it will be like this. Again, it will look like a flow of water. Okay, so in this horizontal portion, whatever the shear flow distribution is, it will cancel each other out so that the net contribution towards the horizontal direction is 0. And the horizontal part components of these things, they'll also cancel each other out in the two legs here. And the vertical components, they will join up together to give a net value of V. Now, in all of these discussions, you have to understand that in this flange portion, okay, in this flange portion, it is very much possible that you can have a non-zero value of the tau xy. So you can have a tau xy like this, you can have a tau xy like this. In this portion also, you can have a tau xy like this, because that is what we have already studied in the beginning of this chapter. So why not present here also? It is very much possible that they are present here. But for all practical purposes, the value of the tau xy will be much smaller than the value of the tau xz, which will be lying parallel to this flange direction. Okay, so the general understanding is like this, that for these kinds of shear flow distributions, you have to remember, first of all, that the way that we are depicting them and understanding them, they work only and only if these walls are thin. Okay, this is extremely important to note. Must be thin, because it is only when they are thin that the contributions from the tau xy, they are negligible. And for all intents and purposes, we can consider that the shear flow in these horizontal parts, they are contributed only and only by the tau xz. Similarly, when you go here, the concept is the same, that the shear flow is contributed by that component of the shear stress which is parallel to the edge direction. In this particular portion, it happens to be the tau xy component of the shear stress. Here, you may still have a component or a shear stress, a non-zero value of the shear stress associated with tau xz. But that value is going to be much smaller than that associated with the tau xy. Okay, so in all of these cross sections where the walls are thin, we are very safe to consider that the shear flow in the various zones will be in a direction which is parallel to the edges. Okay, it works only if here also, it works only if the walls are thin. Okay, so that's all there is to it. This is the theory part, and from our next interactions, we are going to, whether it is recorded or through live sessions, we are going to be discussing problems. All right, thank you very much.